Friends, so you are most welcome to your own YouTube channel. Let's learn. So in the previous videos we have learned how to draw the ILD of simply supported beam, cantilever and overhanging beam. So in this video we'll learn how to use this ILD, or we'll learn how to solve a problem using the ILD. Okay guys, so it will be better if you guys please check my previous videos, because if you guys don't watch my previous videos you will not understand that in this video how I have drawn this ILD, where does the values come from. So these questions will be on your mind, so you will not be able to understand properly. So guys, please watch my previous videos, and the link will be given in the description. So now let's start it. First, suppose AB is a simply supported beam. Okay, RA and RB are the reaction force, and W1, W2, W3, etc. are the loads. Okay, so we'll learn here how to find the reaction force, how to find the shear force, and the bending moment using the ILD. Okay, so we have learned in the previous video the influence diagram of the support reaction RA is like that. Okay, at support reaction at x equal to 0, its value is 1. At x equal to L, its value is 0. Okay, we have learned this in the previous video. So now we have to find the RA, we have to find the value of RA and RB, and the ILD of RB is below. Here it is the diagram of ILD of RB. Okay, and so what is the technique, what is the process? First, to understand, suppose in AB simply supported beam, W1 load is acting at the point D, W2 load is acting at the point C, and W3, W4, etc. Okay, so what we will do, we'll just project these points on the ILD of RA. Okay guys, so let me show you. This is the ILD of RA, and we have to project the points. That is, which points? The points at which W1 is acting. Say I projected it. Let me show it. It is W1, W2 is acting, W3 is acting, and here is W4. Okay, so I projected all the points. Now we have to find the value of ordinates at the points. Okay, what what does it mean? It means the value of y1, y2. That means we have to find these values. Let me show it. We have to find these values. Y1, Y2, Y3, Y4. Okay guys, and after finding the values of Y1, Y2, Y3, we have to multiply with the loads. Okay, now the question is that how we'll find the values of Y1, Y2. So for that we have to use one similar triangle property. So guys, we all remember this property. Suppose if we consider two basic if we consider two basic triangle, that is AGB. Listen, AGB and the triangle DEB. Okay, so see, here is the portion. So from the triangle BDE and triangle BAG, we can write this, that is y by b equal to 1 by L. Now what is the value of 1? 1 is the value of AG. Okay, A equal to 1. We have learned this in the previous video when we are making the ILD of RA. Okay, and the whole distance is L. Now in the similar process we'll find the value of all the ordinates, that is y1 and y2, y3. After the finding of the ordinates, we'll multiply with the loads. Okay, like w1 into y1 plus w2 into y2 plus w3 into y3 plus w4 into y4, and thus we will get the value of RA. By applying the similar process, we can find also the value of RB, and then when we will find the shear force of a particular section, like suppose in section C, we have been asked in the question to find the shear force. Okay, we have to apply the similar process. find, we have to project all the points at which the load is acting, and then we have to find the ordinates, that is y1, y2, y3. Okay, after finding the value of y1, y2, we will multiply with each of the loads. Like here I have written fc equal to w1 into y1 plus w3 into y3. Now the question arises, here we'll get two important cases. Okay, in first case, in the section c, that means in the section where we have to find the shear force, where we have to find the value of the shear force, there is no load acting. And in the second case, there will be a load acting. Okay, now in that case we can see that w1 and w3 are two loads which are acting on the beam. But in the section C, that means in the section at which we will find the shear force, there is no load. Okay, so it is our first case. We will consider it is similar. Then we will find Fc equal to W1 into Y1 plus W3 into Y3. That means after finding the value of Y1 and Y3, all the ordinates, we will multiply them and we can easily solve them. But when we will face case 2, that means in the section C, where we have to find the shear force, there will be already a load acting. Okay guys, just understand this properly. Suppose I have drawn here, in section C I have been asked to find the value of shear force. Okay, and already W2 load is acting at section C. Now what will you do? Here we have to consider two cases again. That is, we have to find the value of shear force at just left of the section C and at just right of section C. Okay. Now for that we have to know the value of the force at section C. Now we have to in the previous video we have discussed how we have proved the values. That is, in section C the value comes minus RB, that is minus A by L. Actually it is minus X by L. Okay, and what is X? X is the distance of the section at which we have to find the shear force, and the distance is considered from the left support A. Okay, so when the section C comes, the value of X becomes A. Okay, then minus RV equal to minus X by L, that is minus A by L, and the positive value also, that is in section C the shear force has two values, one is negative, another is positive, and that is the main problem. Okay, and the value of the positive value of the shear force is Ra, that is B by L. Okay, now what, in the section C we can see two values available. Now which value we will consider when we will try to find the shear force at the left section? At the left section means at just left of the section C, then we will consider the positive value, that means the value of the right section. Okay, and when we will find the shear force at just right of section C, then we will consider the left value, that is the value negative. I have seen here by writing C. Shear force at right of C equal to W1 into Y1. This W1 and W3 has no problem because these loads have unique values, has unique coordinates. But the problem is with W2, because W2 is acting at the section where we will find the shear force. Okay, it is two values. Now shear force at right of section C will use the negative value, and shear force at left of section C will use the positive value. Okay, so in that case we have to find two values of shear force. One is at just right and one is just left. And when we will find the shear force at right, then we have to use the value which is negative. Okay, that means the ordinate which is negative, that is minus A by L. And while finding the left value, we can use the value which is positive. Okay, we have to remember this. And here is the bending moment diagram, that is the influence line diagram for bending moment of simply supported beam. I have drawn here. At section C, the value of ordinate is AB by L. Now what is A and what is B? A is the distance of the section C from left support A, and B is the distance from the support B, that is A plus B equal to L. Okay, so in the section C the value is Now with the help of this value we can easily find the values of y1, y2 and the other ordinates. So up to this we have seen how to find the shear force and bending moment of at any section using the values of the ordinates and the loads. Okay, you have to understand this properly because next we will solve a numerical. Okay, if you guys have any problem in this section, then please watch it again. If you have any problem, then please write in the comment section. Okay, I'll try to help you. But if you guys don't clear this concept, you will not be able to solve any problem. Okay, now next come to a problem. Here we have to know also another concept, that is the concept of UDL. Okay, we have discussed it for the concentrated loads, that is W1, W2, W3, etc. acting, and what did we do? We have we have multiplied the values of loads with the values of ordinates. Okay, that is Fc equal to W1 into Y1, W2 into Y2, and etc. Okay, so and with the help of the standard values, that is AB by L for bending moment, and we have found out the values of y1, y2, and we have done it. Okay, now and the question arises that if UDL x, that is uniform distributed load x, then what will you do? It is different from the concentrated load. Okay, so first we have to find the area. We have to find the area of the span up to which the UDL x. Okay, and then we have to multiply the area with the intensity of load. That is, suppose in that question AB is a simply supported beam given to me. Okay, and this 10 kilonewton per meter, you can see it, 10 kilonewton per meter load UDL x in the span, and the span is I think DE. Okay, up to DE the UDL x. So just see to the shear force, that is the ILD of shear force diagram. From D to E I have marked it. Okay, why I have marked it? Because from D to E I have to find the area. Okay, and it is a trapezium shape. So what will be the area? The area will be half into the summation of the parallel arms, that is minus 1 by 7 plus minus 2 by 7 into the distance, the into the perpendicular distance. That means the distance we will get from this question. Okay, and the another things are similar, like in that portion I found out the values of 1, the values of y, and again the values of y1, y2 I found out with the help of the property of similar triangle. Okay, I have shown it in the previous question, and these are similar. But what is the new, what is the uncommon thing in this question? The thing is that we have to find the area of the UDL, and then after finding the area of the UDL we have to multiply the area with the value of the intensity of the load, that is here 10 kilonewton per meter. We have to multiply with 10. Okay, in the solution we can see that Fc equal to minus 40 into minus 1 by 7. So first what I have done, I have made the projection of all the points at which the loads are acting. Okay, I have seen in the question that 40 kilonewton load is acting at point D. I have drawn it. Okay, and with the help of these values, I have I have found the ordinate of y1 with the help of similar triangle property, and the value of y1 is minus 1 by 7. Okay, I have drawn here C, and up to, from D to E UDL x. I have marked the area because I have to find out the area. Okay, and then again 60 kilonewton load is acting at the point F. I have shown it. I found out the, now in the solution, just see what I have done. Fc equal to minus 40 into minus 1 by 7, that is load, that is 40 into minus 1 by 7, that means it is ordinate. Okay, I multiplied it, and just see it, minus 1 by half into 1 by 7 plus 2 by 7 into 2. Now what is this 2? 2 is the perpendicular distance of the trapezium shape. Okay, I have told you na that we have to find out the area. So the area will be, as it is a trapezium shape, the area will be half into the summation of the parallel arms, that is 1 by 7 plus 2 by 7, and it is the negative side because it is the negative portion. Okay, and the distance and the perpendicular distance between them, yes, between the parallel sides, which is 2. I have shown it here, 2, into the load intensity of the UDL, that is 10. It is for the negative trapezium shape, and again there is also another trapezium which is in the positive zone. Okay, now tell me what will be its area if the ordinates I have given 5 by 7 and 4 by 7. Obviously the area will be half into the summation of parallel arms, that is 5 by 7 plus 4 by 7, particular distance between them, that is 2, I think, 2, into the we have to multiply the load intensity, that is 10, plus 60 into 3 by 7, it is similar, 60 and 80 kilonewtons load are acting, and I have found out the ordinates, that is 3 by 7 for 2 by 7, and we have multiplied this. So using this process I found the value of shear force, and again in a similar process I'll find the value of bending moment also. Just see in the solution, MC equal to 40 in 10 by 7. Now what is 10 by 7? Is the ordinate for bending moment diagram. Okay. And again there is a trapezium. I've drawn it and I found the value. Okay. So you can try it at home. Now the most important part of this chapter, and you can say the most important aim of drawing ILD. What is this? I discussed it earlier that the biggest purpose of drawing ILD is nothing but to find the maximum minimum shear force bending moment. Using the ILD concept, we can design our structures so that we can get the moment and the shear force that much we want. That means we can design it up to our wish, up to our requirement. Okay, it is the main purpose of drawing ILD. It helps us. Now we'll see that how we'll place a load, because ILD is all about moving loads. Okay, we draw shear force, we draw bending moment diagram, uh, we draw everything for the rolling load or moving load. Okay, and the loads are moving, and we just observe the effect of this moving load over the span. Okay, we will find the how the shear force varies, how the bending moment varies. It is our job, it is the aim of ILD. Now in that portion we will discuss how to find the maximum shear force, the maximum positive shear force, maximum negative shear force, maximum absolute shear force, maximum bending moment, maximum absolute bending moment, using the ILD concept. Okay, first I tell you that just I have just told now the maximum bending moment and the absolute maximum bending moment, they are not same, guys. So we will apply different approach to solve them separately. Okay, please don't be confused. I'll discuss them in details now. Okay, now basically we will discuss four case. We'll discuss these four case and find maximum minimum shear force, whatever maximum positive negative shear force, bending moment, maximum bending moment, maximum absolute bending moment, everything we'll discuss under these four cases. Okay, let's understand what is these four cases. First, uh, all the four cases will be applicable for simply supported beam, but using this concept you can also try this for overhanging beam, cantilever beam, etc. Okay, but I'll discuss the topics only for simply supported beam. Okay, so first case, it is the simplest case, that is a load is applied, that is one load, only one single load is applied. Okay, for one concentrated load we'll find maximum shear force, whatever maximum positive negative shear force, maximum bending moment, and maximum absolute bending moment. We'll understand all this under one single load. Okay, so let's see it. Let's see here. What is this? This is a simply supported beam, guys. Okay, and what is this P? P is a load. It is moving from left support to the right support. It is not fixed, it is movable. As I have told earlier that ILD is only applicable for the loads which are moving. Okay, now we know that how to draw the shear force. I mean to say how to draw the ILD for shear force and bending moment. Now I have drawn the ILD for shear force. Okay, the value is AB by L. Sorry, this is the value of bending moment at section C. It has two values, which is no, one is negative and another is positive, guys. You remember this? And the negative value is minus RB. That is RB equal to x by L, and x equal to what? X equal to the distance of the section at which we will find the shear force, that is section C. The distance of section C from the left support A, that is A here. In the question given, the distance is A. That means x equal to A. That is the value is minus RB, that is minus x by L, that is minus A by L. Another positive value is B by L. Okay, we have discussed it so many times in the previous videos. So now just see what happens. We'll understand the cases, we'll understand the technique or the process or the condition at which we will get maximum shear force and the minimum shear force or maximum negative shear force, okay, and the maximum bending moment and absolute maximum bending moment. Okay, just remember one thing: if we have only one single load, just keep the single load at the section itself. Okay, suppose at section C, I have been asked to find the shear force maximum. Okay, just keep this load, just keep the P load or W load, that whatever is applying, whatever is applicable, just keep this load here at section C. Okay, you'll find the maximum shear force and you'll also find the maximum bending moment here. Okay, listen, I have see I have drawn it and I have also given the notes. You can check it, you can write it. Okay. Now we have to discuss absolute maximum bending moment. Now what is this? first first learn the concept. Okay. Suppose AB is the beam. Okay. AB is the span and C is the section where I have been told to where I have been asked to find the maximum shear force, maximum bending moment. Okay. Now to find the absolute maximum bending moment, we have to take the center of the span. Okay, now if we want to find at C, that means what? That means C will be the center of the span. Okay, suppose AP is L, it's L length, then we have to find at L by 2. That means at section C, suppose we are trying to find maximum absolute bending moment. That means C will be at the middle of the span. That is L by 2 from left, L by 2 from right. Okay, now if L by 2, L by 2, that means what? That means A equal to L by 2 and B equal to L by 2, because A is the distance of the section, right? So A equal to L by 2 here. So whatever we do, there is a formula for bending moment coefficient, and for the to find the value of ordinate, what we do? We do AB by L. Now A equal to L by 2, B equal to L by 2. So what will you do? L by 2 into L by 2 divided by L. Okay, that means from here we get L by 4, right? And if we multiply this with W, because we have seen that we multiply the ordinate with the load. In the previous video we have done W1 L1 W2 into Y2, we have did this. So in that case, in this question, now only one load is acting, one single load, that is suppose W load is acting at section C, which is at the center of the span, that is L by 2, L by 2. Now A equal to L by 2, B equal to L by 2. So what will you do? We will just find the maximum bending moment, maximum absolute bending moment, that is L by 2 into L by 2 divided by L. It is the ordinate. This L by 2 into L by 2 divided by L, it is the another form of AB by L. I think you guys understand this. So it is the value of ordinate, and then we will multiply with W. Okay, then we will get WL by 4. Now if we remember that for a single load, for a single concentrated load, whenever we will try to find the maximum bending moment, we definitely get this value in the shear force diagram and bending moment diagram. I think you guys remember this, WL by 4. Okay, so we have found this. We have found maximum shear force condition, maximum bending moment, maximum bending moment condition, and maximum absolute bending moment condition. So I think you have followed one thing. You have noticed that maximum bending moment and absolute maximum bending moment, these two things are not same. Can you please tell me the difference between these two things? Okay, now I tell you the difference, that whenever at section C, uh, suppose at section C, I have been asked in question to find the maximum bending moment. Just read the question properly. Whether it is asked in question maximum bending moment or maximum absolute bending moment. So suppose we have been asked in the question in section C find maximum bending moment. So what load we have? Suppose we have W load, because we are now discussing for a single concentrated load. We have W load. So we'll keep this W load in section C, over section C. So we'll get maximum bending moment here at section C, right? But if we are talking about absolute maximum bending moment, then what we'll have to take? We'll have to take the center of the span, right? Which will be L by 2 into L by 2 divided by L. This is the value of ordinate, right? It is the value of YC, and we'll multiply the load that is acting on the span, on the center of the span, that is W. Then we get WL by 4. I think you have understood the basic difference between maximum absolute bending moment and the maximum bending moment, and we'll also find another way to understand the approach how to solve them in the later portion. Okay, now we'll move to second case. In the second case is, suppose we have a UDL. In the previous case we have discussed we have a single concentrated load, and in the present case we are discussing an UDL. Okay, but this is the UDL. In UDL we'll also have two cases. Okay, in UDL we will have two cases. The first case is that the UDL is longer. Okay, that the UDL is longer than the span of the beam. In the second case, the UDL is shorter than the span of the beam. Now what is this? Let me take an example. Suppose we have a simply supported beam of 10 meter, right? Here I have been shown an example. This is the simply supported beam, suppose AB of 10 meter. But we have an UDL of 12 meter. That means the UDL is acting over the span 12 meter. Okay, its span is 12 meter and the simply supported beam has 10 meter length. So the UDL is longer than the beam span, right? So in that case, what we'll have to do? If we want to find maximum shear force, we must remember the shear force diagram. That means the influence line diagram of shear force. We must remember this. It is like this shape. And just see one thing. In this portion, it's positive value, right? Okay. You don't have any confusion here. And in that portion, it is negative value. Now you just use a very common sense that if we want to have something maximum value, where will we keep this? In positive area or in negative area? Which will be great? The positive area or negative area? Simply you will answer positive area, right? So if the UDL is longer than the span, then we will keep the UDL at the positive area. Why? Because if the positive area is fulfilled by the UDL, it will be obviously fulfilled by the UDL, because the UDL is longer than the span, right? So the area of the UDL will be maximum, and we have discussed it earlier that if we have any UDL, right, to, for the shear force and for the bending moment, to find the shear force, to find the bending moment value, what do we do? We find the area of the UDL, right? We find the area of the UDL and then multiply the load intensity. Suppose W kilonewton per meter load is applying, that is the UDL intensity. We multiply W into the area of the UDL. So if the area is in positive zone, that means what? That means it means the shear force will be maximum. Now vice versa, if we want to find maximum negative shear force or minimum shear force, then what will you do? We will keep the UDL simply over the negative zone. So it will be the negative area will maximum. That means negative shear force will maximum. I hope you understand. Now we want to find the maximum bending moment. Just read the question. We have to find the maximum bending moment, not absolute. Okay. So suppose at section C we want to find maximum bending moment. So we'll draw it, and the section C suppose a distance from left support A. So the coefficient or the ordinate value of bending moment is what? AB by L. We have discussed it earlier. So we'll keep the UDL as mentioned it earlier. The UDL is longer than the beam span. So we will keep this UDL over the full span of the beam. I repeat, we will keep the UDL over the full span of the beam, just like this diagram I have drawn here. Okay, now why we will draw this? It is very common sense that we want maximum bending moment, right guys? And we have UDL. Now we know what? We know for UDL we find the area. We find the area up to which span the UDL is acting, and then we multiply the area with the intensity of load. That means suppose W kilonewton per meter, so we multiply W into the area and we find the bending moment and shear force. Now we'll see that AB is the simply supported beam and the UDL is longer than AB, right? So if we utilize the whole portion of AB, okay, we can do this because the UDL is longer than the beam. So if we utilize the whole portion, the whole span of the beam, will keep the UDL or over the whole span, then automatically the maximum bending moment it will occur, right? Now the question arises, if we want to find maximum absolute bending moment, what will you do? So I think in the previous case, what I have done, in the previous case, I had a load, that means a single concentrated load I had. Okay, now what did I do? For absolute maximum bending moment, I have considered the center, the center of the span. Okay, the center of the span, and I kept this single load over the section C. That means at the center of the span. Now it is similar to this. If we want to find maximum absolute bending moment when we have the UDL which is longer than the span, then what will you do? We'll similarly in the previous case we'll take the middle, we'll take the center of the span. Okay, we'll find AB by L, that is L by 2 into L by 2 by L. Okay, L by 4. Now we'll find absolute maximum bending moment. So just see this, we have to find the area, right? So half into W L into L by 4. Now what is WL? WL means total load, and L by 4 means what? L by 4 means the ordinate, right? The ordinate it is. Okay. So it has been clear, and the answer it comes WL square by 8. Now it's quite similar. Uh, if we remember, whenever we draw any bending moment diagram of simply supported beam which is UDL, you guys remember it? The maximum bending moment which comes equal to W square by 8, it is similar to it is very much similar to that. Okay, so I hope you understood these cases, these two cases. In the next portion I'll discuss the third case. Okay, so before I discuss the third case, please pause my video and just see this first and second cases, because if you guys have any problem over the first and second case, then it will be very difficult for you to understand fourth cases, especially the fourth cases, because in the fourth case we will have several loads, right? So when we will have several loads, we will have Hittel trial method and etc. So I think this will be a little more complex for you so we will first understand these two simple cases better. Okay, so that is the first case and the second case. So first case, the value comes WL by 4. Just remember one thing, if we want to find the absolute maximum bending moment, then we must take the center of the span. Okay, if we have a single concentrated load, or if we have an UDL, okay, when we will find the absolute maximum bending moment, we will find the center of the span and then we will act. If we have single load, then just place the load over the section, sorry, over the center to find the absolute maximum bending moment. And if we have the UDL, just utilize the whole portion of the beam. As UDL is longer than the beam, utilize the whole span, so we will get maximum bending moment. Okay. And if we want to find maximum positive shear force, then place the loads in the positive zone to find the maximum shear force. Now guys, we'll move the third case. The third case is also UDL. I have told you earlier, it's shorter than the span. Now in the second case, what we have seen the UDL is longer than the span. In the third case, we will see the UDL is shorter than the span. Okay, so let's see it guys. So here we have AB, simply supported beam. Okay, and we have this UDL. You can see how I have drawn this UDL, because I have drawn this because the UDL is shorter than the beam. In that case, in this case, in this case, okay. So now let's understand how in this case we will get maximum shear force and maximum bending moment and also maximum absolute bending moment, guys. Okay. So first, for maximum shear force, maximum positive shear force, just remember one thing: if we want to get positive shear force, then the common sense says that we have to keep the load, whatever it is, single load or it is UDL. Whatever we do, we have to place the loads at the positive zone, because if we get the positive zone, that means what? That means the positive area will get, because due to UDL we find the area, then multiply the intensity of load. Okay, then the positive area will get, and the positive shear force, that means the maximum shear force will get. Now place the UDL as I have shown here. Suppose the UDL, it will start from the section C. Suppose in question I have been asked to find the maximum shear force at section C. Okay, and I have been given this UDL. So whatever I will do, I'll start the UDL. I'll start the UDL from section C and then end it. Okay. If the UDL does not end, it does not matter, because my main aim is to find the maximum shear force and I will get it. If it crosses the beam, it does not matter. It is not matter, but the maximum area I will find. I will find the maximum area, maximum positive area, if I keep the load, if I keep the UDL here. It must start from the section C. That means from the section at which we have been asked to find the maximum shear force. Now for maximum negative shear force, it is vice versa. We will start from negative zone. Okay. Now the interesting part, for maximum bending moment. Guys, please focus on this, because you have to understand this very properly. Okay. Suppose AB we have simply supported beam. Okay. And at section C we have been asked to, extremely sorry for the background noise. So at section C, suppose at section C we have been asked to find the maximum bending moment. Now what will you have to see? Just observe AC and BC length. That means the ratio of the length in which the C portion, the C section divides AB. Okay, now let's talk it in the easier way. Suppose AC length equal to A and the BC length equal to B. That means what? That means the section C divides AB at A is to B ratio. I repeat, suppose AC equal to length A, okay, and the portion BC equal to B, the whole length equal to L of the beam, obviously of the beam. So the section C has divided the beam at A is to B ratio. Now we will place the UDL in such a way that the UDL, that the C section will also divide the UDL at A is to B ratio. I repeat, we will place the UDL over the section C in such a way so that the section C will divide the UDL also at A is to B ratio. Now how is this possible? Let's see. Suppose we have placed the UDL in such a way that the ratio of A dash is to B dash. Okay. What is A dash and B dash? It means the length up to which, it means the span up to which the UDL is acting. Okay, from the left of section C, it is A dash, and from the right of section C, it is B dash. A dash is to B dash ratio. Now, according to my theory, A dash, A dash by B dash equal to A by B. So it will mainly distribute in such a manner that A dash by B dash equal to A by B. That means the ratio will be same. Now let me discuss this with an example. Okay, suppose AB, the length of AB equal to 10 meter. Okay, and C is 4 meter distance from left support A. That is AC is to BD equal to 4 is to 6. That is 2 is to 3. Okay, now the section C will distribute the UDL. That means we will place the UDL over section C in such a manner that the left portion of the UDL from the section C will be 2. Suppose UDL has the length, its span over 5 meter. Okay, then it will distribute at 2 is to 3 ratio. That means 2 meter from left and 3 meter from right. That means the ratio will be same. Okay, so now we can find the maximum absolute bending moment here. It is a similar process that we have applied. Find we will find First we will have to find the area, then we'll have to multiply with W. Okay, then if the area has to be found, then we have to apply the law of area of trapezium. as we can see in the diagram, it is a trapezium shape. Then what will be the area? The area will half into the summation of the parallel arms of the parallel sides into the distance, into the perpendicular distance between them. So I have done this, you can check it. And there are two trapeziums. Okay, so I multiplied with 2, thus I found the area. And now case 4, suppose I have two load P1 and P2, and P2 load is leading. That means P2 is before, or you can say that it comes first, then P1. Okay, and the distance between P1 and P2 is equal to X. Okay, and the distance is fixed. Okay, P1 and P2 are two moving loads, which are in that case P2 is leading. That means P2 comes first. That means in any section, if the loads are moving from left to right, P2 will pass the section first, then it is the turn of P1 load. Okay, and the distance between the P1 and P2 loads are X. It is fixed. The distance is fixed. Now we'll have to find maximum shear force. We have to know that how we'll place the loads so that we'll get our desirable shear force, bending moment, etc. Right? So in the shear force, suppose first P1 is more than P2. That means P1 the load is greater than P2. Then we'll place P1 load at the section. At which section? At this section, we'll have to find the maximum shear force. So P1 will be placed here, and P2 will be placed at the right. That means at the positive zone. Okay. Now stand for maximum bending moment. It is quite similar. We have to apply two hit and trial method, because it is confirmed that P1 load is at section C. Now we don't know that P2 will act over right side or left side, because both sides are positive. So we have to apply hit and trial method. It is the first case that P2 is the right portion of section C, and it is the second case that P2 is at the left portion. We have to check. We have to check that which bending moment has maximum value. Okay. Now the most important question that arises. Suppose we have a train of load. Now what is a train of load? It is nothing but it is a collection of load, or you can say that several loads together. Okay, like that question we have. Let me show you. This is a train load. Here we see 15 kilonewton, 10 kilonewton, 12 kilonewton, 10 kilonewton. 4 loads are total acting. Okay, and the distance between the loads are also given. Okay, so it is called the train of a load. That means several concentrated load are acting. Now we have to find the maximum shear force, maximum positive, maximum negative shear force, maximum bending moment, maximum absolute bending moment for these loads. Okay, now in that case we have to use so many numbers of detailed trial methods, but I'll tell you the most general two cases for finding the maximum shear force. You will find you will get 99% probability of finding maximum shear force between these two cases. Okay, rest if the loads are heavier or the loads are lighter in some special cases, I'll tell you, you have to apply, you have to use another hit and trial method to check, just to check. Okay, now first, like this question, 15 kilonewton, 10, 12 and 10. Okay, now first this 15 kilonewton you apply at the section C. Suppose you are given at question a section C and you are asked to find maximum shear force. Okay, now keep all the loads at positive zone. Okay, just 15 kilonewton at the section C and 10 kilonewton at the distance. According to the distance it is given in the question, right? Suppose in this question 10 kilonewton was 1.5 meter away from 15 kilonewton, 12 kilonewton was 2 meter away from this load, and 10 kilonewton was 1.5 meter from the 12 kilonewton. Same the distance it will be followed here. 15 kilonewton, just keep the 15 kilonewton load at the section C and all the loads at the right section of C, that means in the positive zone. Okay, now we have to check another case. Keep the second load if the second load is heavier. Suppose in this question 15 kilonewton is the first load and 10 kilonewton second load, but the 10 kilonewton load is not heavier, 15 is heavier. Okay, so we don't have to utilize the second hit trial. We'll get the maximum share the first case. That is, this is the answer. In this manner, if we place the loads, that means 15 kN at section C, and another load at the right, that means at the positive, we will get maximum shear force. But in such case, there may be like this question: 10 kN is the first load, then 15, 12, 10. The second load, just check. Second load, that means 15 kN load is heavier than 10, right? So we will have to check it by keeping the 15 kN. That means the heavier load at section C. Okay. Now the 10 kN will act over the left portion. That means the negative will get another shear force. Just check whether this shear force is maximum or not. Okay. Now we will get our maximum shear force in these two cases. First, the first case, in the first load that is given, whether it is heavier or light, just keep this at section C and all the loads at positive zone. And second, which load is heavier? Suppose the second load is heavier, then we will keep the second load at section C. Okay. In this manner, the 10 kiloton, that means the first load, which was not heavier than 15 kilonewton, it is acting over the negative zone. We have to check whether this shear force is maximum or this shear force. Okay. Now it will trial method. Now the question arises, how we will find maximum bending moment or maximum absolute bending moment. Now guys, I tell you one thing, in such questions, that means where a train of load or several loads, several concentrated loads are given, maximum students get confused how to find the maximum value of bending moment or maximum absolute bending moment. It is because why in some books or in some PDFs we'll find mixed way. They do the common solution so that we get confused how to solve them separately. I'll tell you the separate approach, the different approach for solving the bending moment, for solving only bending moment and absolute bending moment in separate way. And next I'll solve a problem using the techniques. Okay, so I think you guys have understood the concept of shear force properly. Now it's time for bending moment. Okay, now just see what I have written to approach. One, find maximum bending moment section which is given, and second, find absolute maximum bending moment, not the section, not the load or not the location given. Now how will find the difference between the questions which will be given to us? We have to understand the first difference. Okay, suppose we have been given a section, a particular section. We have been asked in the question. Suppose section C is given and the distance will be mentioned. Suppose it is 8 meter distance from left support M. It will be mentioned in the question, and we have to find the maximum bending moment at that section. That means what? The section is known to us. Okay, we know the section, we know the location. We have to just find the load under which the maximum bending moment occurs. I repeat, in that case, in the first case, the location we know. That means the section at which we have to find maximum bending moment. We know this. This will be given in our question. But we have to find the maximum. We have to find the load. We have to find the critical load under which the maximum bending moment occurs. That means we have to understand which load we will keep at this section so that we will find maximum bending moment, right? So let's see this example. Suppose W1, W2, W3 and W4. These four loads are given and it is a load system. So we have to compare, we have to and what is this? This is a train of load. It is passing, okay, it is passing from left support A to right support B. Okay, I will pass all the loads one by one to over the section C, over the section which is given in the question. Okay, I repeat, suppose okay, in that AB simply supported beam, the section C is given, which is a distance from left support A, right? So we have been asked in this section C, the section is known, and in this section C, we have to find the maximum bending moment. Now we don't know which load we'll have to apply on this point so that we get maximum bending moment. So we'll pass all the four loads one by one over the section. First, in our first case, we will move this W4 because it is leading, right? First W4, then W3, then W2, then W1. I'll tell you the condition at which we will stop. Okay. First, W4 load is moving. It is passing the section C. Okay. Now just see this diagram. as I have said, the W4 load is moving over the span and it is passing the section C. Now, the, if we see the left support, if we see the left portion of section C, then we will find W1, W2, W3. There are three loads acting, okay, in the left portion, and in the right portion only one load. There is W4 is acting. Now what you have to do, we have to check WL by A. A means what? A means the left support, A means the distance of the section C from the left support A. Okay. Now we have to check WL by A. What is WL? WL means the summation of the left loads. Okay. Now in this diagram we can see in the first case when W4 load is passing, when W4 load is passing, the loads at left portion acting are W1, W2 and W3. So here WL equal to summation of left loads, that means W1 plus W2 plus W3 divided by A. On the other side we will find WR by B. Now what is B? B is the distance of the section from the right support B. Okay, so we will find WR. WR means what? WR means the summation of the right loads of the section C. Okay. Now in the diagram we can see that at the right of section C only one load is acting. That means W4. So here WR equal to W4 by B. Now we have to check WL by A or WR by B. If WL by A is more than WR by B, then we will repeat the condition. That means in first case we pass W4 load over the section C. In second case we will pass W3 load over the section C. That means we have to compare first WL by A and WR by B. Okay, we have to compare between these two things. If we get WL by A is more than WR by B, just focus on this condition. If WL by A is more than WR by B, then what we have to do? We have to move on. We have to move W3 load, we have to pass W3 load over the section C. Okay. Now just see the diagram. Over the left portion of section C, W1 and W2 loads are acting, right? And over the right section, W3 and W4, these two loads are acting. Then if we find again WL by A, that means WL means the summation of the left loads. Left means left from section C. Okay. Then WL equal to W1 plus W2 divided by A, and WR means what? W3 plus W4 divided by B. We'll again check. Now if we find that WL by A is less than WR by B, now this W3 load is the critical load, and if we find it is more than, then we have to repeat this. That means we'll have to move W2 load again. That means W2 will pass the section C. That means we'll have to find again WL by A and again WR by L, and here WL will be only W1, and W2 plus W3 plus W4 will be what? WR. Okay, so it is the process. Okay, so in this process what we have to think first, suppose first WL by A is more than WR by B, and in the second case, that means when W3 load was passing from the section C, WL by A is less than WR by B, then we can tell that W3 is the critical load. That means if we place the W3 load at the section C, we will find maximum bending moment. Okay, so let's understand this problem with an example. Just see, here we have a load system 80 kilonewton, 160 kilonewton, again 160 and 120. The distance are given 2 meter, 2 meter and 3 meter. Okay, I will I will show you the same load system and the same beam and the same problem. I will show you how to find absolute bending moment so that you guys don't be confused. Okay, just see, as I have told you, to find the maximum bending moment. Okay, a section will be given to me in the question, and here the section C is given. Okay, the section C is 8 meter distance from the left support A. Okay, then first case we have to pass the first load. The first load, that means the load which is leading the train, that means 120 kilonewton. We have to pass the 120 kilonewton over the section C. That means at the left, here it will be 80 kilonewton, 160 and 160, and at the right of section C here will be only 120 kilonewton. Okay, then we'll have to find what we find. We find WL by A and WR by B. Okay, so what means WL? WL means the summation of the left loads. That means the summation of the loads that are acting over the left portion of section C, right? So in first case, as I have passed the first load, that means 120 kilonewton over the section C, then WL means 80 plus 160 plus 160 divided by A. M is here 8. Okay, then we get 50. 50 is more than what? 50 is more than WR by 17. What is 17? The value of B is 17. 17 because S equal to 8 and the whole portion A equal to 25, and the portion C, that means B equal to 25 minus 8, that means 17. Okay, then 120 by 17, 7.05. 50 is more than 7.05, right? So here we have to repeat the process. That means in second case we have to pass 160. That means this 160, right? This 160 we have to pass over the section C, right? So again we have to check if this 160 we pass over the section C. Just imagine that the left portion, what are the loads? 80 kilonewton and 160, and over the right portion this 160 and 120, because because 160 load is just passed over the section C right now. So in the right portion there will be two loads, 160 and 120, right? And over the left portion 80 and 160. So again find WL by 8. So WL means 80 plus 160 divided by 8 is 40, and WR by 17 is coming 16.4, right? So it is more than, again it is more than. Then what we have to do? We have to repeat the process again. That means we have to move now this 160. Don't be confused. In the second case we moved this 160 kilonewton over the section C, and it is coming again more than. That means again we have found WL by 8, WL by A is more than WR by B. Then we have to move to the third case. Next step, this 160 kilonewton will be passed over the section C, right? So if we pass this 160 kilonewton over section C, the left portion only one load will be there, 80 kilonewton, right? So where I have shown it, I have shown the calculation right here. WL by 8 by 8, 10 coming, and in the right portion there are three loads. That means 160, 160 and 120. So I have found the WR by, that means the summation of the right loads, 160 plus 160 plus 120 divided by 7. Divided by 17, that means B. Here I am getting WL by A is less than WR by B. That means it is the critical load. That means the second 160 kilonewton is a critical load. How did I understand? I understood because in the third case, when I have passed this 160 kilonewton, that means second 160 kilonewton over the section C, we found that WL by A is less than WR by B, right? And before that condition, we found WL by A is more than WR by B. In all the cases, all the above cases, we found this. But in that case, when second 160 kilonewton passed over the section C, we found that WL by A is less than WR by B. That means it is the critical load. That means this is the load which we have to apply over section C so that we get maximum bending moment, right? So I have drawn it 160 section C, and then as the load system is given, the first 160 is 2 meter away from this, 120 is 3 meter away, 80 is 2 meter away. Then according to the rule which I have taught you earlier, we have to find the maximum bending moment. That means we have to multiply the load into the ordinate. That means we have to find the value of y1, y2 and y3, and we can find the values of y1, y2, y3, all the ordinates, with the help of the property of similar triangle, right? I have shown here. Suppose y1 by 6, we have to find this distance. We have to check within two triangle and use the property of similar triangle, right? So we will find the value of ordinates and we will multiply. 80 into y1 plus 160 into yc. That means the value of yc equal to what? AB by L, A equal to 8, B equal to 17, 8 into 17 divided by 25 is coming 5.44, right? So thus I have found the maximum bending moment. If you guys have any problem in finding the ordinates, please tell me in the comment section. I'll help you. This is the similar property triangle I have used. Listen, suppose in the first triangle here, and it is the first triangle, and the whole portion is the big triangle. That means the value of y1 is coming 4.08 by y1 by 6 equal to 5.44 divided by 8. Similar way, I found all the ordinates and I multiplied the value of ordinates with the load, and I found the maximum bending moment 2425.6. Please do the numerical at your home and check the value. Okay. Now I am moving to the next part where I have been asked to find absolute maximum bending moment. In the previous part, I have found the maximum bending moment. Okay, so now I will find the absolute maximum bending moment. How I will do it? First, we have to note the 3 points. Absolute maximum bending moment always occurs under a wheel load. That means um, the portion at which absolute maximum bending moment will occur, here must be a load. It will not happen that between two loads the maximum moment is coming. No, it is not right. We must have any load acting over the section where the absolute maximum bending moment is coming, right? Now the second point, absolute maximum bending moment occurs near the center of the span. Okay, so in the first two cases, I think you guys remember when I have taken the first concentrated load, one concentrated load, and also UDL, we take in consideration the center of the span, right? To find the maximum absolute bending moment. But when we will find maximum absolute bending moment for for several concentrated load, that means for a train of load, that means the problem which are facing now. Okay, in that condition, in this situation, it is not necessary that the bending moment, that the absolute maximum bending moment will always occur at the center of the span. Okay, it may occur at the near of the center where the heavier load will act. Okay, it depends on the loads. It depends on the load's intensity, the value of load, and the direction also. I'll tell the whole process. That condition generally absolute maximum bending moment occurs under the heavier load near to the center of gravity. We will find the center of gravity, it will be discussed in the process. But the main point which we must remember to find the solution of this type of problem is the distance of the center of gravity of uh, the distance of the center of gravity from the center of span equal to the distance of the load under which maximum bending moment takes place. Achha. Let me explain this thing. Here please add one thing, the distance of center of gravity of the load system. That means in question a load system will be given to us, right? That I have shown here. Suppose this is the load system 80, 160, 160, 120. It will be given in a question. So we'll have to find the center of gravity, right? And what we have to follow the rule, and the rule is the distance of the center of gravity of the load system from the center of span. We'll also find the center of span, and we'll find the center of gravity of the load system. Just guys, please be focused. Don't be confused between these two things. One is the center of gravity of the load system, another is the center of the span. Okay, these two things are not same. One is the load system, which will be given in our question like this. Like this, it is the load system W1, W2, W3, W4. The four loads are acting. So the load system will find the center of gravity. Okay, and we will also find the center of the span. Here it is a section Suppose AB is a simply supported beam. Okay, we'll find the center of this span, and we have to follow this rule. What is the rule? The distance of the center of gravity of the from the center of span equal to the distance of the load under which bending moment will occur. Okay, we have to find this. We have to know at which load the maximum absolute bending moment will occur and at which location we will place it. Okay, so please speak focused on thing. I'm discussing the process. Okay, first, the first step we have to follow: find the center of gravity of the given load system from right and check which load is nearer to center of gravity. Okay, I will discuss it with an example so that you guys will understand this better. Find the distance of the center of gravity of load system and the nearer load D. Now what is this? First I have to find the center of gravity of the load system. I'll try to find the center of gravity from the right. Okay, from the. I'm extremely sorry for the disturbance. So I'll try to find the center of gravity of the load system from the right. Okay. Now I am showing you an example. Suppose there the previous question I have solved, it was for maximum bending moment at a section which was given to me, right? So in that portion we'll solve the absolute maximum bending moment 80, 80, 160, 160, 120, 2 meter, 2 meter, 3 meter. Okay. First First step, find the center of gravity of the load system from the right. Now, from the 120, the distance will be 0 because it is acting on the point at the right corner. From 160, the distance is 3 meter, right? And from this 160, the distance is 2 plus 3, that is 5 meter. 160 into 5 plus, what is the distance from 80? 2 plus 2 plus 3, that means 7. 7. And the summation of the loads 80 plus 160 plus 116 plus 120, right? The center of gravity is coming 3.53 meter. So this 3.53 meter is considered from the right portion, right? Now if we find the distance between the center of gravity and the load, now just see one thing. This 160 kilonewton is nearer to the center of gravity, right? And it is also heavier, right? It has matched the both conditions. First, it is nearer to the CG of the load system. Second, it is heavier. So we have understood this. Under this 160 kilonewton, we will find the absolute maximum bending moment, right? Now the condition is that we have to find the distance from the center of gravity to the load, to the 160 kilonewton load, and the distance is 0.53 meter. How this came? This came from, see, let me show you. Suppose somewhere here the center of gravity of the load system is acting. Okay, the distance from here is 3.53 meter. Now if I say the distance from this portion is 3 meter, now what is this extra portion will be 0.53 meter, right? So I have shown it 0.53 meter. What is this? This is the distance from the center of gravity of the load from the load, that is from the 160 kilonewton load under which we will get absolute maximum bending moment, right? Now we'll place this. Guys, be focused. This is the most important part of the question. It is our second step. Sorry, it is the third step maybe. We'll place this 160 kilonewton load at 0.53 by 2 distance, 0.53 divided by 2 meter distance from the center of the span. I have already discussed the steps, the basic steps to solve this question. In first step we will find the CG and we will check which load is nearer to the CG. We have found the CG. The CG is coming 3.53 meter, okay, from right. We also saw that what is the which load. We see that 160 kilonewton is nearer to the center of gravity. How did it is nearer? We have also shown it. Now the second step is find the distance of the center of gravity of the load and the nearer load. Okay. In this question, we have found the distance between the center of gravity of the load and 160 kilonewton. The distance is coming 0.53 meter. Now the third and the last and the most important step. Okay, the step is now place the load at d by 2 distance from right from the center of the span, so that the center of gravity will remain d by 2 distance left from the center. Find absolute maximum bending moment. Guys, I think you guys did not understand this. Let me clarify. I think you guys remember before I have discussed the one condition, one basic rule. That means the distance of the center of gravity from the center of span is equal to the distance of the load at which the maximum bending moment will occur, right? It has to be followed. We must follow this. Now, in that condition, what I have said keep the distance, that is place the 160 kilonewton, that means the load at which we will get maximum absolute bending moment. Keep the 160 kilonewton at 0.53 distance, right, at the right portion, at the right section from section C, 0.53 divided by 2 meter away from section C. Now automatically center of gravity will remain also 0.53 meter 0.53 divided by 2 meter away from the section C from left. Okay, in the other sense, I can say that the center of the span is at the middle. The center of the span is at the middle, at the in between the load 160 kilonewton, under which absolute maximum bending moment we will get, and the center of gravity. So it is followed, and then we have to place these loads like that. 160 kilonewton is acting at D. What is D? The distance of D is 0.269 from section C. That means 0.53 divided by 2. Now, if we measure the distance from A, it will be what? It will be 12.5 plus 0.269. Means it is 0.269 distance from the section C, and from left support A it is 12.5 divided plus 0.269. The distance is coming 12.769, right? We'll also here A is 12.769, B is what? 25 minus 12.769, that is 12.231 is coming. It is a basic calculation part of this question. Mainly you have understood the concept and you can solve the questions, right? So we have find YC. YC, how we find? AB by L, that means AB equal to here 12.769, that means it is coming from adding 12.5, that means the distance of center, plus 0.53 divided by 2, that is plus 0.26, right? So here it is coming. We have found the value of YC. With the help of value YC, using the similar property triangle, we can find all the ordinates like y1, y2, y3, and then we will get absolute maximum bending moment by we'll multiply the loads with the ordinates, right? So in that manner we will solve this type of question. So please practice this type of question. It is very much important for ILD, and this chapter is almost over. If you guys have any problem to solve these questions, please tell me in the comment section. I'll try my level best to help you. On the next video, I'll discuss the influence line diagram of indeterminate structure, and then truss also. It is remaining truss. Now the simply supported beam is over. We'll discuss how to draw ILD, how to solve problem, and all this. So guys, thank you very much for watching my video. And if you guys think that my video is beneficial for you, especially for the civil engineering students, so please like, comment, share, subscribe my channel, and don't forget to press the bell icon, so that you will get all the notifications when I will upload my new video with the new content, which will surely provide you some knowledge. Okay, so guys, thank you very much. Goodbye.